Okay, so we are very happy to have Jay Armas from Amsterdam talking to us about a very interesting topic connecting black holes in generalized gravity theories and soft matter, like in the picture we have some blood cells. So yes, so I hope it will be very interesting. So over to you then.
Yes. Thanks a lot for the invitation. It's a pleasure to speak to all of you. So I'm going to speak about some connections between black holes and soft matter systems by means of non-relativistic geometry. So this work is mostly based on this paper here that was published in PRE with Jelle Hartong, Emil Heo, Bjarke Nielsen, and Niels Obers. I think I will also have time to discuss a bit of my work with Akash Jain on some generalization of some aspects of this. And then I will also mention some of my earlier work that somehow motivated this many years later. So I should make it clear that yeah, my background is in string theory, but I got interested in soft matter, which is a completely different field, and the motivations for this work in specific is not really so much string theory, but more, you know, what can the tools of string theory contribute to these other fields, in this case soft matter. So the motivations are mostly to sort of understand soft matter systems. Um, and you would like, in general, to understand, you know, how to model the response of continuous media at long wavelengths. So in the context of relativistic physics, we know for many years how to do this in a controlled framework using effective field theory, derivative expansion, gradient expansion, and symmetries as guiding principles. This is not an approach that is very much sort of followed in soft matter communities. It's becoming more and more so, but it's not the standard approach to problems. It's more a phenomenological approach. And I'm specifically interested in describing Galilean invariant systems, but also systems that break some of the symmetries, which are those which are pertinent to this kind of systems in soft matter. And then I'm also interested in sort of describing those systems in curved geometries, in curved backgrounds. So again, in relativistic systems, we're used to this. We can put the fluid on any specific curved geometry. But well, in that case, maybe the applications of this are less less physical. But in the non-relativistic setting, the world is basically curved. You can think about surface of water waves. You can think about droplets. You can think about fluid membranes. There's also systems or physical phenomena of cell migration. For instance, when the cells are trying to heal some wound in your skin, this can also be described by some kind of flow at long time scales and also on curved geometries. And then as a byproduct of sort of this research, you can try, you know, you can have a framework for describing boundaries, branes, interfaces, and defects in Galilean invariant theories, because you sort of have to describe how to couple specific surfaces or describe surfaces embedded in Newton-Cartan geometries. This is sort of some of the systems that people consider in soft matter. So this is work by some experimentalists that show how to artificially construct toroidal geometries. So they can construct pretty much almost any shape with almost arbitrary genus, and they can spin it around, and they can even put, you know, active particles on it, sort of bacteria swimming on it, and they can study how these flows happen on these geometries. So this is already experimental setups that are known for a while. And of course, because of these setups, it means that you actually have the possibility of studying flows on these curved geometries. This is another example, a bit more
Jay,
recent.
could you
Yes.
explain what was the previous slide? Actually, this t is equal to what is happening in this as time here?
This is the way they produce or they make these things. They take some sort of cellular or some sort of shape they can easily make, a circular shape, and then they're kind of puncturing it with something, with this thing here, and they're able to put a hole on it that is still stable under sufficiently long time scales. So that's yeah. Of course, I don't know all the details of how do they, you know, what solutions they use and stuff for creating these cells, but this is what they're doing. They're drilling a hole on it and making it stable. This is sort of the same kind of construction, but now they put a different solution on it, if you may. So this is a kind of liquid crystal structure here. It's called active pneumatics. So it's a structure that evolves with some dynamics on the curved surface. And this is also something that people are trying to understand in all sorts of ways, with topological analysis and also new frameworks for fluid dynamics, for how these active pneumatics flow. There's more down-to-earth applications about this. If you just think about describing surfaces, waves on the surface of the Earth, that's a curved geometry. These sort of more detailed structures you see here of different color are the so-called Kelvin and Yanai waves that are sort of confined to the surface equator, the Earth's equator, and they're responsible for certain defects like El Nino oscillations and so on. So this is something that geophysicists look at, and of course, you know, trying to formulate these frameworks in curved geometries can also sort of make these analysis a bit more rigorous in the high energy, from a high energy point of view. Another more down-to-earth application is the so-called lipid bilayers, which are sort of membranes that are formed out of specific components. In this case, they have a polar head and a hydrophobic tail. So the tail doesn't like water. It hides here in the middle, and then the polar head constitutes the surface of the membrane. And this is pretty much the type of structures that you have in the cells inside the body. And an influential piece of work in this direction has been the Helfrich action, which is a sort of free energy that has to be minimized to find different shapes of cells inside the body. So here, this is a simple, this alpha is a simple surface tension. In a way, it's very much related to the Nambu-Goto action. This is just the surface tension. Of course, this here is just spatial curvature. It doesn't involve time or anything, but it's surface tension. And then there is some interaction terms, if you want, which are proportional to the extrinsic curvature. This is the mean extrinsic curvature. And this C0 here is called the spontaneous curvature. It's sort of the tendency that the system has to bend in a specific way under deformations. And then if you minimize this action and you find its shapes, it apparently actually describes many of the shapes you see under the microscope. So people have seen, for instance, spherical topology cells. This is a liposome. You can find spherical topology as a solution of those equations. Another one is torite. You can find this also as a potential cell. So it's a torus. And then the famous one is this discoid, this biconcave shape, which is a sort of red blood cell, which apparently has exactly the shape that action predicts. And of course, there has been like multiple generalizations of that action to anisotropy and pneumatic phases and smectic phases and all sorts of other configurations and systems. But the goals that I have and this sort of direction has brought me to is to try to develop a framework in which symmetry organizing principles can be used to model equilibrium Galilean invariant systems. So these are the types of actions that I just showed you. Is something that I want to model in a sort of framework that we recognize. For instance, we couple some field theory to some background, and we can write that action in, using symmetry principles. Then I also want to understand how such systems evolve as they depart from equilibrium. So what happens if I poke it a little bit? How does it evolve? And then I'm also interested in modeling active systems using symmetry principles. So active systems are systems in which you have some sort of elements or constituents that are self-propelled. So you imagine that you put some bacteria in some fluid. Those bacteria somehow are self-propelled. They have activity, they have its own life, and they move around in the fluid. And you can sort of model this in a long wavelength regime using also symmetry principles. Okay, so
Jay, can I ask something?
yeah.
So in this, maybe you're going to say till later, you showed this action where there's a k plus c0 square term, but why not a linear term in k separately? Or
because the linear term in K is not parity invariant under the change of normal.
okay, I
So
see.
it's a requirement on, well, I mean, I'm not saying that there aren't systems that are not parity invariant, but apparently not these ones, yeah. So
Thanks.
that has this constraint, yeah. So the plan is that I want to show is you know, how do you model the analog system using relativistic symmetries, and then you can sort of do a null reduction, which it's a type of reduction that we're used to already for a while in even in the context of ADS-CFT, that we can perform some specific transformations along a null killing vector, and we can reduce the system to a system that has non-relativistic symmetries. But you can also construct this from scratch if you basically define what submanifolds and their deformations are in Newton-Cartan geometry. And then I'm going to give you an examples of how you use this machinery to build these models from scratch. And then if I have time, I will say a few words about breaking boost symmetry, which is sort of the road towards describing active systems. So relativistic counterpart, and this is how I was led to this. This is sort of a depiction of a black ring. Is a black hole in 5 dimensions. Solutions of Einstein is a solution of Einstein's gravity in 5 dimensions, pure gravity. It has S1 cross S2 horizon topology. It has 2 radius, inner radius R, and then this radius R0 of the S2. So this is kind of, every point here is an S2. And it's rotating. If it was not rotating, it would collapse. So it's rotating. And if you increase the angular momentum very, very much, like very, very, very much, you end up in something called the ultraspinning regime, in which the angular momentum is much bigger than the mass of the ring. And then the ring becomes like very, very thin. Thin in the sense that the radius, the inner radius is much larger than this local radius of the S2. And then if you zoom locally of the geometry near this ring, you find that this is the geometry of a boosted black string. So this is something that was already figured out in 2007, and then in 2009 was made more precise. And this, funny enough, if you want to describe what is the sort of deformations of this string, how you deform this string and build it slowly into a ring by making some sort of perturbation on the string, you end up realizing that you're actually dealing with some kind of fluid theory. This fluid theory is described by a stress tensor, here with the hat, that has a delta function piece. So it's a piece that is confined to the surface or the wall volume of that string. And that stress tensor has a usual expansion in relativistic hydrodynamics. It has an energy density, a pressure, a fluid velocity, If you think about what is a fluid velocity interpretation in terms of the string, it's a boost. So it's a Lorentz boost that changes locally. It has a pressure or tension in the gravitational language. And then you also have viscosities and so shear and bulk viscosity, etc. But you get another piece here, which is a derivative of a delta function. So these are usually called finite thickness effects in string theory, when you have a thick brane. And this correction here that you see with the thickness comes with a specific structure of 3 indices, which is called the bending moment. It's something that is proportional to a 4 tensor called an elasticity tensor, and contracted with the extrinsic curvature, which is a kind of strain. So when you bend some black hole slightly, it sort of behaves a bit like an elastic medium. And this is what characterizes its response. So this is true with black holes in flat space, in higher dimensions. So black holes in string theory, black branes, they all have this structure, more complicated, higher form symmetries, blah, blah, but the structure is the same. And you're also sort of known, or you know about the ADS-CFT correspondence and the fluid gravity correspondence, in which, for example, you have a curved black hole in the bulk of ADS. And then if you inflate this curved black hole very, very much, meaning that you take the large mass limit, in which the mass of the black hole is much larger than the ADS scale, then locally, you know, this is described by a planar ADS black brane. That also gets corrected if you take higher corrections in this large mass black hole. And those higher corrections and the framework that describes these deformations is just fluid dynamics on the boundary. In this case, there's no bending, there's no thick brane kind of thing. Everything is happening on the boundary. It's a different setup, but you still get fluid dynamics. Now, you can build effective theories that describe either the deformations of these black holes in flat space or in ADS, whatnot. And you can describe those, or you can define those equations for any kind of configurations that you think of the fluid. It could be time independent, or it could be time dependent. But solving the equations is much simpler if you focus on stationary configurations, so time independent configurations. And then there is a theorem, a well-known theorem, that tells you that if it's time independent, then the fluid velocity has to be aligned with a Killing vector field k mu of the background. And k here is the modulus, because this has to be unit normalized. And as a consequence of that, the bulk or the expansion of the fluid, theta, which is the gradient of the velocity, vanishes, and the shear tensor vanishes automatically. And there's no entropy production. That's why it's in stationary equilibrium. When that happens, it was shown by Minvala, Bhattacharya, and others that you can actually write an equilibrium partition function. In this case, without boundaries, I'm assuming no boundaries. And you can write an equilibrium partition function that you correct with derivatives, depending on the accuracy that you want the effective theory to describe. To ideal order is just the pressure. In generic dimensions, there is no first order corrections. And then as you go up to second order corrections, you get the term that is proportional to the acceleration square, vorticity square, and the curvature of the geometry where the fluid is living. If you think about the ADS CFT correspondence, this would be the curvature of the boundary geometry. Now, this sort of equilibrium partition function is built just out of symmetries and a gradient expansion. So to write these partition functions, you have to classify all sorts of scalars, which are Lorentz invariant, that you can write at a given order in derivatives. And in this case, in this simple case, it happens to be just 3, which is the acceleration squared, vorticity squared, and the Ricci scalar. And you obtain the stress tensor, the fluid stress tensor, by just doing a variation with respect to the metric. Now, you could think about the same thing for droplets, relativistic droplets. So these are sort of systems in which they have a boundary, an interface. The fluid is not living everywhere in space. When you think about this in the context of ADS, this doesn't make much sense because there's nothing there to give you a boundary in the boundary metric. But if you think about Shirk-Schwarz ADS, then you do have some boundary there, a natural boundary. And there you can find these sort of things called plasma balls that also have gravitational duals. And so this was sort of the motivation for this relativistic story. And what happens is that besides this bulk action that you have in the bulk of the droplet, you have to add a surface action that has a surface tension. And then there's possible sort of couplings you can add. One is the extrinsic curvature. Again, this is linear, so if you want parity invariance, it's not there. And then this is a sort of what is called a parity odd contribution, because I'm focusing on 3 dimensions. So this is a parity odd contribution. And this is sort of a contribution due to the normal acceleration of the velocity. So this is how you would do if you include boundaries. Now, the
what
other
is
thing,
new here?
new.
L, the vector L?
L is just the normal odd vector you can write in 3 dimensions, which is the epsilon Levi-Civita tensor in 3 dimensions, contracted with 1 copy of the fluid velocity, contracted with the vorticity.
It's a dual of the vorticity.
Yes, exactly. The dual of the vorticity. So this term you would also write a similar term in the bulk if you had a 3-dimensional bulk and you wanted to include parity odd contributions. But now here the bulk is 4-dimensional and the boundary is 3-dimensional. That's why I can write this. So this is a story for droplets. But now for describing those sort of black holes that I've showed you in the beginning, in which there's some thickness corrections because yeah.
Sorry, I also have another confusion in this action. So are
Yeah.
there no boundary conditions thought about here? I mean, is there?
Yeah, the boundary condition here is that the component of the fluid velocity along the normal direction vanishes. So the fluid is not sort of trying to rupture the interface. It's moving. It's sort of there's no normal component to the fluid at the interface. Mm-hmm. That's the only boundary condition. You can actually show that this is the right boundary condition from an entropy current analysis, outside equilibrium.
Okay.
It fixes this. It's a kind of Goldstone-like equation that you can derive from entropy currents.
So without this, you won't have a stable equilibrium anyway, right? If you're
at least not in the relativistic case. I'm not entirely sure if the non-relativistic case would have different conditions. I never studied that, but the relativistic case, we proved that using entropy current methods, this is the only reasonable thing you can have. Yeah.
Thank you.
Yeah. So the other situation I want is one in which there is no bulk. It's not a droplet. It's just the interface. That's called a fluid membrane. You can think about it as a soap film. If you stretch a soap film, that's a fluid membrane. Effectively, a soap film is like a 2-dimensional surface because the thickness is just, too small compared with the size of the film. And at the scales you're looking at, you don't care about the thickness. So in that case, I just have a surface. And so I don't have a bulk part. There's nothing inside. It's not a droplet. And what can I write in that case? Plenty of stuff. So I have the pressure, and then I have acceleration square, vorticity, and Ricci scalar. But these are geometric quantities associated with the surface. So this Ricci scalar here is the curvature of the surface, not the curvature of the spacetime. And then you have a bunch of other couplings, as you can see here, lambda 1, lambda 2, lambda 3, that are proportional to combinations of the extrinsic curvature. So there's 3 such combinations of the extrinsic curvature tensor that you can write. These are these 3 ones. So actually, these sort of curvatures, these combinations have been written in the context of the fine structure of string theory by Polyakov in the 80s and by Kleinert. But here there's more combinations because you also have the fluid velocity. So there's more possible contractions. And then these terms that you see here, which are proportional to this omega A here, which is not the vorticity, it's the extrinsic or the spin connection of the surface. So the spin connection is something that tells you how the normal vectors are being twisted around as you move along the surface. So these things are defined by what's is called the Weingarten identities. You take a covariant derivative of a specific tensor. Here, the specific tensor is the tangent vectors, and you get a world volume connection or a surface connection and an extrinsic curvature. But if you take a derivative of the normal vectors, then you get an extrinsic curvature and the spin connection. So these are basically decomposing different parts of the background connection in terms of geometric quantities that make sense on the surface of the geometry. And there's two sort of cases you can write here. One is just proportional, is linear in the extrinsic, is linear in the spin connection, and the other is quadratic. These terms here, they sort of describe the spin. So you can have a string, let's say, that is spinning on the transverse directions. And that spin is basically these terms here. So the closest system that you can think of is a spinning point particle. What is the action of a spinning point particle? Well, it would be a mass term, just like the pressure here. And then it would have this term here that would give you the spin. So the spin would be this var pi 1. That's the action of a spinning point particle. But here is a brane, so it can spin in different directions, etc., etc. Yeah.
Sorry, I have a very basic question here. So what is it an action of? Because in the previous slide, the only degree of freedom was a velocity vector and perhaps a temperature too, because P is a function of temperature.
Yeah, so here the degrees of freedom, yeah, if you think about the fluid theory, the degrees of freedom are just the temperature and the fluid velocity. That's true. But once you have an interface, even here, this is the interface, there is going to be a bunch of scalars that will describe the position of that interface. Those are extra degrees of freedom. And those extra degrees of freedom are encoded here. That's why I have an xi here. This is very much like the Namugoto action or the Polyakov action. These extra scalars, they're transverse scalars that describe the position of the interface. Now those scalars, they're not solved for. Like they are something you have to solve for. You have to minimize this action with respect to the scalars to find the shape of the configuration. You see?
Okay, yeah, okay. So well, in that case, these are dynamical, one should think
dynamical fields, yeah, the dynamical
fields.
Yeah, they're like goldstones of spontaneously broken symmetries, but they only make sense at the location, at the surface. They're not like broken everywhere in space, just where the location of the surface is. Yeah. Okay, that's how you see it.
So one could think as is a free energy where you minimize the velocity and this excise to minimize.
Well, the velocity has already been minimized, so to speak, because you focused on equilibrium. So you've chosen velocity to be aligned with the killing vector. That's sort of solved. The fluid degrees of freedom are solved in sort of in equilibrium partition functions. There's nothing to do about it. It
would not be the only solution, right? I mean, that's an assumption, but the velocity.
It's an equilibrium assumption. That's unique. Like that's the theorem I showed. Like equilibrium requires killing vector. It requires fluid velocity aligned with killing vector field.
Yeah, but I mean, in that case, for example, if you take certain manifolds, the vorticity can just simply vanish most of the term. So, I mean,
sorry.
So I think in the original paper of
the vorticity doesn't necessarily vanish when you have equilibrium configurations. So only the shear and the expansion.
Yeah, but yeah, okay, maybe we should talk about. I mean, this so far suggests an assumption like the U will align with the killing vector at equilibrium.
It's not an assumption.
There can be other.
No. That's a hard and fast, steady, proven theorem that if you have equilibrium, killing vector field is aligned with. Fluid velocity is aligned with killing vector field. There's no way out.
And how do you prove that? I mean, just.
Well, you ask, what is the requirement of equilibrium? Is a time-independent background, right? So if it is a time-independent background, there has to be a killing vector field that annihilates the background. So that's one thing. The other thing is, an equilibrium configuration is a configuration that does not dissipate. If you look at the entropy production of any configuration, that entropy production is proportional to expansion of the fluid squared and the shear squared. So you have to choose a configuration. Equilibrium configuration is a configuration for which theta squared and sigma squared has to vanish. The only possibility is if U is aligned with the killing vector field. That's it's just
I understand that, but suppose if I view it as some free energy that I should minimize, there's no guarantee that the killing vector would actually minimize the free energy, right? In that case, of course, equilibrium.
But this free energy is built upon the assumption that the fluid velocity is aligned with the killing vector. So there's no equilibrium free energy if there is no killing vector. Now you can write an effective action, a Schwinger-Keldysh effective action, in which makes no assumptions on what the fluid velocity is. And in that case, you get the whole plethora of dissipative transport. But if you want just the equilibrium part of that transport, you require the fluid velocity to be aligned with the killing vector. That's how it works.
Okay.
I mean, we can talk more about it, but the only assumption I made was equilibrium. Yeah. So from this action here, you can derive what is called the bending moment, which is the derivative of the action with respect to the extrinsic curvature, and the spin current, derivative of the action with respect to the spin connection. And the equations of motion are rather complicated, but they are what they are. So this is what you get by reparametrization invariance. So this is just a very non-trivial identity that the action satisfies along the world volume directions. And then this is sort of the dynamical equation. This second one is a dynamical equation you have to solve to find the shape of the geometry, of the interface or the surface, whatever you want to call it. So they're complicated equations, but in many cases you can sort of solve them or perturbatively, etc. It's possible. So if you want to find black holes with these equations, there's all sorts of things you can do. This is called the Black Helicoid. You have to minimize that action and try to look for a helicoidal geometry. Apparently that exists. It's a solution with topology R cross SD minus 3. It's supposed to exist in just pure Einstein gravity. And then if you want to find this in plane wave geometries, you can find all sorts of things, helicoids and catenoids and everything in between. Now, what I want to do is not to talk about black holes anymore, but to understand, why do I want soft matter and how did that came there, is because this action here is very reminiscent to that first action that I showed you about the red blood cells and the soft matter systems. So the first thing you can do is to think, well, what is a non-relativistic counterpart of this action? And indeed, you could just perform a null reduction of this action and find a Galilean invariant theory. And that Galilean invariant theory would give me the free energy in equilibrium for fluid membranes that I would have to minimize to find the shape of. Now, instead of doing that null reduction, I'm going to follow a bottom-up approach. And I'm just going to set up the problem in Newton-Cartan geometry, because this is more clean in any case. So what I have to do basically is to describe Newton-Cartan submanifolds. And this had not been done until this paper that I mentioned in the beginning. So a Newton-Cartan structure is sort of a non-Riemannian geometry that is described by the following structures. This is a clock one form. It's called the clock one form. It's a kind of time-like Wielbein. This is a spatial structure, a spatial two tensor, which is not exactly a metric. I will explain why. And there is a sort of a U1 gauge field, also called a mass connection. And there is what is called a Newton-Cartan velocity, V, and a contra metric, a spatial metric. And so this is not exactly Riemannian geometry, which means that you cannot just use a combination of these structures and find a metric that involves both space and time. You cannot do that, otherwise you'll be in the realm of Riemannian geometry. Instead, you have to work with all these structures and their transformation properties. Now, once you have these structures, you introduce these sort of completeness relations. So this is the delta function is described in this following way here, with the Newton-Cartan velocity and the clock one form, and these guys are normalized to -1. You introduce a set of Wielbeins, spatial Wielbeins. These indices with a bar are local tangent indices of the Wielbeins. And the spatial metric or spatial two tensor is described by just the contraction of the delta function with the spatial Wielbeins. The contra metric is the same thing with the indices up. And then there is this sort of relations of the Wielbein. So the sort of time-like Wielbein with the index up annihilates the spatial Wielbein, and the time-like Wielbein with the index down annihilates the spatial Wielbein as well. And if you contract these two, you get a delta function. Now, these structures, they transform according to certain symmetries. So in relativistic geometry, these local tangent indices would transform under Lorentz boosts and rotations, etc. But now, because you're in Newton-Cartan geometry, what the symmetries are rotations and Galilean boosts, and also transformations of this mass gauge field, which is like a gauge transformation. Now, it's possible to define structures that are sort of invariant under boost transformations. These are these sort of hatted geometries. The reason why this is important is that at the end of the day, you want to find or develop an effective field theory framework that respects all symmetries. So you want the structures that you are writing to be invariant under local symmetries, in this case, boosts. So you want to work with these sort of kind of structures that are invariant. And then you define the geometry by the so-called Wielbein postulates. So the covariant derivative annihilates the contra metric and the time-like Wielbein. And this allows you to formulate actually a whole family of connections. And you can pick one which is sort of easy to work with, which you can write in terms of boost invariant, partially in terms of boost invariant structures. The transformations, becomes more obvious what I meant by these transformations, of all these structures are according to the following equations that you see here. So the time-like Wielbein with the index down just transforms under diffeomorphisms in the natural way with the Lie derivative of a diffeomorphism transformation. With the index up, it transforms also with a diffeomorphism, but then it transforms with a boost. This is a boost parameter in the tangent space. The spatial Wielbeins here transform with a diffeomorphism, with a rotation matrix, and with a boost. With the index up, transforms with just rotations. And the mass gauge field transforms with a diffeomorphism, with a boost, and with a gauge transformation. This sigma is like a gauge parameter. The contra metric as you can see here, just transforms with diffeomorphism. So it's really a sort of metric in the true sense, because it's invariant under all other symmetries. The metric with the indices down, on the other hand, is not a metric. That's why it's not supposed to be called a metric, but a two tensor, because it transforms under boost transformations. So it's not invariant under that. And the boost invariant structures, as you can see here, this metric bar with the indices down, doesn't transform under boosts, but does transform under gauge transformations. So these boost invariant structures are boost invariant, but at the expense that they're not invariant under mass gauge transformations. It's either one or the other in Newton-Cartan geometry. You can have it all. So
yeah. These the mass gauge transformations from the relativistic point of view?
Yeah.
This gauge transformations, what are they from the?
So these gauge transformations, they're sort of diffeomorphisms of the null direction, because you have to start with a d plus 2 theory, in which you add an extra direction, and it's the transformations of that extra direction that act as sort of a, yeah.
Okay, thanks a lot.
That's where it comes from. So in this sort of background, I want to put a brain on it, some surface. I want to couple a surface to this geometry, in the same way that we put a string in Riemannian space. And this geometry has a p+1 wall volume, so it has a codimension d minus p. I'm doing this for general codimension, even though in the end, for soft matter stuff, I want codimension 1. But I'm doing it for arbitrary codimension. So what do I have to do? I have to do exactly the same that I would do in a relativistic case. I have a world volume here, p+1 dimensional. I introduce a set of mapping fields, so the embedding map, that tells me what is the position of this surface in the ambient space. Then, as soon as I have the embedding map, I can define the tangent vectors. They're just derivatives of the scalar fields. They're explicitly defined. And then you define the normal vectors implicitly by the conditions that it must be orthogonal to the tangent vectors and unit normalized in all directions. This doesn't define the normal vectors uniquely, because you still have SO d minus p freedom of rotating these normal vectors with a rotational, with this matrix here, and these conditions are unchanged. In fact, this should be like, this should be instead O d minus p, because you can actually change the sign of the normal vectors and nothing would change. So there's that freedom there. Then there's completeness relations. So again, delta function is given by a combination of tangent and normal vectors, and the normal vectors and tangent vectors, etc. They sort of obey orthogonality conditions and completeness relations. So here there's nothing standard. There's nothing out of the ordinary. It's just normal, as you would do in relativistic structures. Now you could think about the following question, which is what we do in the Riemannian case, which is, what is the geometry on the surface? When we ask this question in the Riemannian case, the geometry on the surface is just a pullback of the geometry of the background. So if I want to know what's the induced metric on the surface, I take the background metric and I pull it back with the tangent vectors here. Now this gives me a Riemannian geometry on the surface in the case of the Riemannian case, but it doesn't give me a non-Riemannian geometry in the case of Newton-Cartan. You have to work a bit harder to find what that is. So I'm going to focus on time-like submanifolds. And by that, I mean that the clock one form, when you pull it back, or when you contract that clock one form with the tangent vector, it is purely tangential, in the sense that the normal component of the clock one form vanishes. So this is what you would say it's a time-like manifold. It's just moving straight up in time. So the normal vectors here are purely spatial. And this has several implications. You work them out. So this means that the normal component of this contra metric is just delta ij, that the mixed component vanishes, that the 2 tensor with the normal indices is the delta function, and the mixed index 2 tensor is proportional to the normal component of the Newton-Cartan velocity and the tangential component of the clock-1 form. So you have some basic building blocks for this geometry, which are these ones here. This metric, the pullback of this metric, the clock-1, the Newton-Cartan velocity, the countermetric with the indices up, the mass gauge field, and this transverse velocity. Now, the background, Newton-Cartan geometry, satisfies this condition. It's the orthogonality between the Newton-Cartan velocity and the spatial metric. However, the induced structure does not. If I just take the induced Newton-Cartan velocity contracted with the induced 2 tensor, I get something which is proportional to the normal component of the velocity. This means that if I just pull back the structures of the background onto the surface, I don't get a Newton-Cartan geometry induced on the surface. In fact, you need to define a new quantity, which I call this H check AB, that has this specific combination. And in that case, you do get a completeness relation, and you get this condition that the background satisfies. So I had to fiddle a little bit with the building blocks that I had, which is the different contractions of the background structure, to build what you would call an induced 2 tensor on the surface that respects the Newton-Cartan symmetries. And you can sort of do the same sort of games as you do with the background and introduce boost invariant quantities. So here they're defined as H bar. They have the same structure as the background quantities, but now with these checked quantities that I need to define in order to have exactly the same transformations, Newton-Cartan transformations on the surface as I have in the bulk of this in the Newton-Cartan spacetime. Then I have to define induced geometries. I have to define the calculus, covariant derivatives, connections, etc. And I do that implicitly by saying, you know, if I have a specific tensor with a world volume index, I can split it in derivatives in this way, in which this gamma is the connection of the induced geometry on the surface. This is the background connection. And the induced geometry on the surface is given by, the connection is given by this expression, which is exactly analogous to how the background connection is defined in terms of background quantities. And then you introduce the so-called Weingarten identities to define, again, the extrinsic curvature and the spin connection of this Newton-Cartan submanifold, which is given in this specific way. So this is the extrinsic curvature. That is the spin connection, which you can also write in given a specific combination in terms of the torsion tensor, which is this TAB. So the extrinsic curvature is defined in this specific way, which is exactly analogous to the way you define in Riemannian geometry, except that there is some sort of considerations you need to make regarding the position of the indices in this tensor. So this is almost all that I need for describing the geometry. I also need to derive the so-called integrability conditions that relate the intrinsic geometry to the extrinsic geometry or to the background geometry. And there's 3 such conditions: the Codazzi-Mainardi condition, which relates the derivative of 2 extrinsic curvatures with respect to the Riemann tensor of the background, certain components of it. There's the Gauss-Codazzi relation, which is more well known. This relates the Riemann tensor of the surface to the Riemann tensor of the background and contractions of the extrinsic curvature. And this one, which is slightly more obscure normally because it's only there if you have a non-trivial amount of codimensions, so more than 2, is called the Richievos equation, that describes basically the curvature tensor associated with the spin connection. So this is kind of a field strength for the spin connection, related to other components of the Riemann tensor of the background and more extrinsic curvatures. Then you need to derive the whole calculus of how to vary these structures, because at the end of the day, you're going to have some action that geometrically depends on these structures, and you need to know how to derive it. So you need to work out variations of the embedding map. You need to work out diffeomorphisms. I won't bother you so much with the details, but this is possible to do. And it gives you certain relations when you act with these transformations on the given structures. So what I want to do really is to define an effective action given certain structures. And here the fundamental structures are the clock-one form, the metric boost invariant metric or two tensor with the indices down, and the extrinsic curvature. I could also add the spin connection, I could add the Ricci curvatures, etc., but this is a simplified case that I'm interested in. And then the variation of the action is just the response given the variation of these three fields, which I define here with an energy current, a mass, a stress mass tensor, and the bending moment, which is the response to the extrinsic curvature. Then there's also gauge invariance, in the sense that you need to require this action to be invariant under mass gauge transformations. That gives you this conservation of the mass current. And you also want to require this action to be invariant under rotations of the normal vectors. That gives you this sort of condition. It's a kind of integrability condition that you also see in elasticity theory. And then there is momentum conservation, which is what you get by requiring this action to be reparametrization invariant. It gives you this condition here, which is automatically satisfied, given that the action is by construction reparametrization invariant. So this is just a non-trivial set of identities on the action. And then there's the dynamics, which you get by varying with respect to the transverse scalars, the position of the surface. And it gives you this equation here, which is very similar to the equation I showed you in your relativistic case, except that now we're dealing with just Newton-Cartan structures.
Sorry, I couldn't follow the last point, because you assume some specific action here, or is it?
No, it's just general. I just assume an action that depends on these three structures. So that's all. That's the only assumption that I make.
Yeah, I understand that. But then, how do we get this last? What is this D, by the way?
The D is the response to variations of the extrinsic curvature.
Ah, okay,
So
I see.
it's here.
Okay, but then this last equation, how do we get this last? How can we have a very general?
I just need to know how do these structures here, the variations of TA, AJB bar, and KABI, how do they vary when I vary the embedding map? So I can work this out precisely. Like here, I'm showing you how this TA is varying. It varies like this. And then there's a more complicated equation for KABI, etc. But I can work them out. And if I work them out and I package them, it gives me this. Using a bunch of identities, etc. You put it like this. So this is the general solution if you have an action that just depends on these geometric structures. General equation in motion.
So essentially, it is because it captures some redundancy, because after all, everything is coming from some shape, and so this is what gives rise to this last equation. Essentially, the fact that all this, there's some degree of redundancy in these definitions.
No. This equation is really just what is the equation? Where are the dynamics of the scalar fields, right? So the redundancy is actually in the momentum conservation, because p plus one of those scalar fields are surface directions, and if you demand your action to be reparametrization invariant, there is p plus one redundancies. And that's why you get this equation here, which is trivially satisfied. But what is not redundant is the transverse components, the transverse directions. So all the scalars in the remaining codimensions, those have dynamical equations. And this is what you get from from varying with respect to those.
Yeah, okay, thanks. But my major confusion was that if you change the action, the equation doesn't change. That's what I was confused.
Well, as long as the action is just built out of these structures. Yeah.
So what does the action actually capture if it doesn't give any dynamics as such? It's just a tool to compute this TA, TAB, and TABIs.
Right, and to solve and to give you the dynamic equation to solve.
I see. But so it is just basically yeah, okay, it's okay. Okay, thanks. Now I understand.
I mean, I'll show you in an example. Maybe that becomes clear. But all I want to do is to find different shapes, and I need to know what equation that I need to solve to find those shapes, given some assumptions of symmetries. So this is what I'm trying to do. So examples here. I want to describe a thermal state in equilibrium, and this again. I go back to fluid theory, in which we know how to do this. And here, a thermal state is described by an equilibrium killing vector field, which is this Ku, is described by a specific choice of boost transformation parameter and a gauge parameter. What this means is that given that there must be a choice of these parameters such that the action on the structures that I have on the induced Newton-Cartan structure vanish. If I find a solution to this parameter such that this thing vanishes, I find equilibrium. And indeed, given those specific conditions, I can define scalars that are boost invariant. There's only two of those. One is the temperature, which is constructed in the following way. And the other is the chemical potential, which here is kind of a velocity field or a velocity potential, so to speak, which is given in terms of this structure here. So there's both the gauge parameter here, and there is a boost invariant quantity that is contracted with two copies of the fluid velocity, and the fluid velocity again is aligned with the killing vector field. So there's two scalars I can write in equilibrium. These are the two. And so I can build an action that is based just on these geometric quantities. The simplest one is just something that is proportional to the surface tension of the membrane. So this is the surface tension, which is a function of the temperature and the chemical potential. I can define thermodynamic relations. So the entropy is just the derivative of that thing with respect to the temperature, the number density, the derivative of the surface tension with respect to the chemical potential, and I get what is called the Euler relation, as is expected from fluid dynamics. And then you can obtain the currents. Again, this was part of your question, like, what does this help you do? Yeah, you obtain the currents by performing a variation with respect to those sources, the TA and the AJB, and you get the energy current and the mass stress energy there, which is very similar to a fluid mass stress energy. And the dynamics in this case are quite simple. It just says this has to be equal to 0, which implies this specific combination here needs to vanish. If you didn't have a fluid velocity, so if this term was 0, then what this equation gives you is just a minimal surface equation. This is sort of well known, like if you have a fluid film and you want to know what is the shape that it takes, it's a minimal surface shape. So this is what you do. You can put boundary conditions, etc., but you have to satisfy a minimal surface equation. Once you have a fluid that can also move in that film, then there is a contribution, which is this one here, that sort of tells you, what is the centrifugal repulsion. If you have a fluid that rotates on the film, it's going to have some centrifugal acceleration that has to be balanced by the tension of the film. So this is what it gives you here. Actually, you can write this specific combination as the normal acceleration of the fluid. So it's really like a centrifugal repulsion. Let's make a small sort of exercise here, which is to understand where are the dynamics away from equilibrium. So I had an equilibrium partition function. I can describe equilibrium. It tells me that this equation is so and so. I can solve this equation very, very easily. The most trivial solution that I can find is a plane. A plane has zero extrinsic curvature because it's just flat. So this equation is trivial. And now I can ask, well, what happens if I slightly deform the surface? This is the same as saying, you have the skin of a drum, and you want to, pull it a little bit and see what are the oscillations of the skin of the drum. And you do this by just deforming the equation, like you make a deformation of your equation along the surface direction. So the transverse scalars, you deform, you shift the transverse scalars by a small amount, and you ask, what is the solution to this equation? And what you find is that you have to solve this wave equation here, and the solution is a linear dispersion relation that you find in a common textbook. Of course, here minus chi, I'm assuming that my chi is negative. That's why I have a minus there, which is the opposite conventions to normal textbooks. But what this dispersion relation gives you is exactly the the elastic waves that you find in a textbook when you look at what are the waves propagating on the skin of a drum. It's the same as in a fluid membrane. It's these dispersion relations that are proportional to the square root of the surface tension. So this is giving you the right dynamics, which you could not get if you hadn't included the fluid degrees of freedom. Because if you don't have the fluid degrees of freedom, you will never get this fluid velocity there. In other words, if you don't use Newton-Cartan geometry, you won't get the dynamics right. If you just use Euclidean geometry to describe just a spatial slice of the surface, you won't get the dynamics right. Droplets are similar. It's exactly the same structure, but now you add, an internal pressure. So you can add an internal pressure and an external pressure. If you think about the droplet that is sort of inside is water, outside is air, or in both sides is just air at different pressures, then you get something which is the Young-Laplace law, where the right-hand side is the variation of the pressure with respect to external and internal. And then this is one of the main points of what I wanted to show, is that now you can also try to work out what is this Helfrich energy from a Newton-Cartan point of view. And in that case, there is a surface tension, as you can see here, but there is also the extrinsic curvature, the linear extrinsic curvature, which you can remove by parity invariance. And then there is k squared and k dot k without other terms that are proportional to the fluid velocity, which you could also add here. But already at this stage, this free energy is is a generalization of the free energy that Helfrich wrote in the 70s. So that free energy was this here, but the coefficients do not take into account the detailed structure. It doesn't take into account the fact that the temperature actually has a geometric interpretation, and doesn't take into account that the chemical potential or the modulus of the velocity is also a scalar that depends on geometric properties in equilibrium. So if you do not do that, you just consider these coefficients as being some constants, but in fact, they are not necessarily constants. They have a geometric interpretation in thermal equilibrium. And as such, you are going to get modified dynamics and modified even equilibrium equations because of that non-trivial dependence on the geometric structure. So this is what I want to show, mostly because it tells you that this can be actually useful to model these kind of systems because these symmetry approaches haven't been used and using this sort of background and coupling the fluid to a given background geometry. So I have some things to say about breaking boost invariance, but I'm not sure if I have time, or maybe you can tell me if I'm too much already out of time.
Well, we can have 5 more minutes, 5 or some more, because we can
I,
take some
I,
afterwards.
okay, 5 minutes then. I go quickly. So the breaking boost invariant. So I've been talking about Galilean geometry and Galilean boost invariants, and now I want to break it. And the reason I want to break it is because of these systems you see here. So these are flocks of birds and schools of fish here. And here is just a bunch of bacteria moving around with some self-propelled energy. And these systems, they break boost symmetry because they're moving with respect to some reference frame. There is some medium in the background, air, and these guys and these sort of collective behavior is sort of moving through that medium. So there is no way that you can sort of boost and go and move with that flock. So the boost symmetry is like explicitly broken in these systems, and they're all over the place. Now, in '98, Toner and Tu, they wrote down a model, which is the model that has been widely studied in soft matter for describing active systems. This is just part of that model, is the sort of corresponding Navier-Stokes equations. And the way they wrote this model was not, so to speak, in the way that a hydrodynamicist in high energy would do. They basically wrote down all possible sort of vectors you could add in a specific equation, and just added one by one with arbitrary coefficients. So these coefficients, they return to something that we understand when you reduce to a Galilean invariant system. But here they're left arbitrary because somehow you broke boost symmetry, and so these coefficients have the freedom to be different. Now here there's terms that are similar to what we know. So this is sort of viscosities in different directions with different gradients, etc. And this term is what people call the active term. So this is a term that is proportional to the velocity. It breaks what we understand as a derivative expansion, because if you see here, the left-hand side has one derivative and this term has 0 derivatives. But this is kind of the driving force. It's what drives the system. It's like the energy that is put in there for the birds to sort of being able to fly, or the fish to be able to swim, etc., etc. And these terms here, they not only, so there's not only breaking of boost symmetry, but there's also break of space-time translations, explicit breaking of space-time translations, which I'm not going to talk about so much, but I want to talk about the breaking of boost symmetry. And what happens is that now you need what is called Aristotelian structure. It's not a Newton-Cartan structure because it doesn't have Galilean boost symmetry. Boosts are not present. So the structure is pretty much the same as in the Newton-Cartan case, but the difference is how they transform. So if I go here, these were the transformations in the Newton-Cartan. If you can see here, there's the boosts, etc. But now, in an Aristotelian case, these guys, these boosts, are just not there. Neither this specific gauge transformation. So this is called an Aristotelian geometry, and it doesn't transform under boosts. It's just, you remove them if you want. And now you need to couple, geometry and fluids to this structure, not to the Newton-Cartan structure, if you don't want to assume boost symmetry. Now, I'm not going to give you all the details again, because I just have very little time. But what happens is that your fluid dynamics is modified from the beginning, because now the velocity itself, the velocity that now you should interpret it as the velocity of the flock, is itself a thermodynamic quantity. So here the sort of Gibbs law that tells you what is the gradients of pressure is the usual terms with the temperature and the chemical potential, but now there is this term which is directly related to the velocity of the flock. And this is a kind of dual momentum, which is just the density times the velocity of the flock. So this becomes a thermodynamic quantity because you broke the symmetry. And then you can play these games about how to construct the first order theory and how many transport coefficients there are. And I'm just giving you some sort of flashing out some things. So there is some dissipative corrections to the stress, dissipative corrections to the energy current, dissipative corrections to the charge current. And these corrections come with a bunch of coefficients, these B's and S's, etc. In fact, there's like 17 such structures. So it's a big theory in which you can take all sorts of limits. If you try to restore boost symmetry, you can restore Galilean boost symmetry, and you get the Galilean invariant system. You can restore Lorentz boost symmetry, and you get a Lorentz invariant theory. Or you can even choose specific other types of scaling, like Lifshitz scaling, and you get a Lifshitz fluid. So it's kind of a master theory that gives you all these limits. But it's also the theory that you have to work with if you break boost symmetry generically. And the funny thing about this is that what is the spectrum? Like if I want to know what are the sound modes in this theory, I have to fluctuate the equations, make small deformations, and you find this collection here of sound modes, and you find three sort of diffusion, you find one diffusion, charge diffusion mode, and two shear modes. This shear here is a shear in direction sort of along the flocking velocity, and this one transverse to it. And the funny thing is that the sound modes, normally sound modes are parity invariant. So there's always a sound mode traveling to the right and the sound mode traveling to the left with equal speeds, because you have either Galilean boost symmetry or Lorentz symmetry. You can always boost in either one direction or the other, and it's always the same. Now, in a non-boost invariant theory, what happens is that the sound modes are actually different if you move along the flock or against the flock. So you can see here that this part here under the square root has a plus and a minus, but the correction, that there is some correction, here the angle cos of theta is the angle between the flocking velocity and the plane wave perturbation, the wave number. And you can see that the contribution is the same for both cases, meaning that there is one velocity which is bigger than the other. So there's two speeds traveling at, two sound modes traveling at different speeds, which is a fun physical effect that you find in these systems. And then there's there's two shear modes, which normally in a Lorentz invariant theory or Galilean invariant theory are the same, are also different. These coefficients are different exactly because there's shear along the flock and shear transverse to it. I'm just showing the shear transverse mode. It has a simple structure because the other ones are really not something I want to present. So I finished. So what's my outlook? What I would like to do further? I would like to find solutions to that generalized Helfrich energy of rotating fluids, which haven't been found. I want to include other fluid degrees of freedom in that free energy because I haven't considered the most general free energy that you could, given the symmetries. And that hasn't been sort of considered in the literature. I want to study the stability of specific membranes. So can I study the stability of a spherical membrane, the stability of a biconcave membrane, etc., just to answer simple questions like, are red blood cells stable or not? I also want to describe the full dissipative effective action. So this would be using Schwinger-Keldysh effective field theory. And then you could also do something that I haven't done, which is like boost breaking membranes. So the membranes I described were Galilean invariant, but now I could couple them to Aristotelian geometry and find geometries or surfaces that also break boosts, and then describe also other phases of matter, like liquid crystals, viscoelasticity, etc. And then in the case of boost breaking, I also want to derive that Toner 2 model from effective field theory. Instead of postulating that there is these and these terms, I just want to derive what is the most general thing. And there I need to sort of also break space-time symmetries, and I need to understand how do I incorporate that breaking of space-time symmetries in the Schringer-Keldysh formalism so that I don't sort of make any mistakes in how to formulate the effective field theory, because we just don't know exactly what are the rules of the games when we include space-time symmetry breaking and driving terms and so on, with all these different patterns of symmetry breaking, like boost symmetry breaking. It just becomes complicated, and you need to do this rigorously if you want to do this completely. So yes, thank you for your attention.
Thanks a lot. It's a great talk.
Thank you.
So we have time for questions, of course. Let's have a few. Okay, so maybe I have a question here. So you said that if you put a fluid on some topology, some kind of membrane, the fluid actually couples, the velocity of the fluid will couple to the shape, and it can alter that.
Yes.
So
yeah, it's just that the stress tensor now has extra components that did not have if you didn't consider the dependence on of the coefficients on the temperature and the chemical potential.
Yes, right. But when you're talking about active matter, for example, if you think about like a swarm of bacteria moving in some fluid, similarly, the action of the bacteria can also change the fluid medium itself on which it is moving, or some. So you do not know that, or
well, I don't have the whole theory of active matter penned out in this language. I mean, because as I said, if I want to describe those interactions, I really need to understand how to incorporate the driving forces,
okay,
etc. in this thing. But in any case, at the level of the effective theory, I mean, you're looking at long wavelengths, right? And you don't assume that. Well, it's not that you don't assume. I mean, there's of course a effect of the flocking velocity on the shape of the surface. I mean, there will the equilibrium configurations that you will find will of course depend non-trivial on that velocity. Yeah, that's a fact.
Yeah,
I don't expect to find the same shapes, equilibrium shapes in the theory without flocking as in the theory with flocking.
mm-hmm.
Yeah, so there'll be a non-trivial interaction for sure.
Yeah, I just wanted to point out that I kind of heard a talk where they were claiming that if you, for a swimming bacteria, can actually change the viscosity of the medium in which there's flocking or swimming. And there is some.
Yeah, now I think you're thinking about, like, you know, what are the actual transport coefficients. So then the microscopic calculation that you have to do to find those transport coefficients can be completely different. And yeah, I mean, the viscosity that you will get in an active case can be very different than the viscosity you get in a non-active case. But that is not something I have an answer to, because I'm on the macro theory, so I just put like arbitrary coefficients. I have no idea what.
No, they also have, I think, some kind of macro theory. Just they take into account how I had the. Well, I probably. I think it's just about understanding how the flock also can affect the medium, something like that. And they have.
I'm not familiar with the macroscopics of this. I'm not familiar. I know that there is some attempts at getting this, but I'm not sure how well they're under control. Yeah.
And can some of these effects be also understood if you have in the context of black holes, like you can put
I mean, the activity, I'm not sure.
No, not that. The first part of the talk, like you said, okay, you
well, yeah, but then you go back into the question of what is the what is the gravitational theory that would describe Newton-Cartan fluids on the boundary.
That's what
on the boundary, and I don't think this is known, right? I mean, no one has formulated this in any way that is reasonable.
I see.
There's some control under Lifshitz theories, because you can take them as limits of ADS, but not the Newton-Cartan, pure Newton-Cartan geometry. So that would be something I would definitely be interested just for the fun of it, but it's not even something I know exactly how to do or how to even begin.
Because I think there are many people working on this Newton-Cartan variations of gravity itself, right? And
yeah, exactly. So they might, at the end of the day, have something related to that. It might be something like putting that in the context of some holography, maybe. But at this point, as far as I'm aware, no one has a very good idea of how to do that in practice. But I would definitely be interested in trying to figure that out. Yeah.
Okay.
Yeah.
Okay. So thanks a lot for this, and I really enjoyed the talk. And
you're welcome.
Okay. So have a nice rest of the week. And
yes, yes, you too. Bye bye.
Thank you.
Bye.
Bye.